Neutral atom lattices are one of the various qubit architectures for quantum computing. In terms of intellectual origin, as with all qubit architectures, Feynman's lectures on quantum computing and the DiFincenzo criteria lay the foundation and outlined the criteria to be explored for neutral atom qubits. However, before we can get into how this system can satisfy the DiFincenzo criteria, there are a few additional scientific discoveries that were absolutely key to enabling neutral atoms to be pursued as a potential candidate for a qubit architecture. The first was absolutely crucial, and this was the invention of laser cooling and trapping, for which the Nobel Prize was awarded in 1997. Laser cooling, which relies on the momentum imparted when a photon is absorbed and the randomness of the direction that the photon is then emitted, reduces the velocity of gas atoms, which are initially traveling near 300 meters per second at room temperature, thus decreasing their thermal energy until their temperature is on the order of microkelvins. This discovery allowed atoms to be localized, without which operations on single specific atoms would not be possible. Another important achievement for neutral atom computing was the superfluid Mott-Insulator transition. Once the atoms are laser cooled, they must then be arranged into a lattice configuration. There are a variety of ways to achieve this, in one of which lattice nodes act as potential wells, created by intersecting laser beams, which then interfere. However, due to atomic collisions, only sites which initially contain an odd number of atoms end up occupied by a single atom, whereas most sites containing even numbers end up empty. This results in only about 60% population of the lattice sites. While this can manually be corrected through additional lasers, which can be used as optical tweezers to move the atoms back into place, there is an alternative method to populating lattice sites. And this method is the Mott-Insulator. The atoms initially are prepared in a Bose-Einstein condensate, which is a very cold state of matter in which bosons are all in the same ground state. The Bose-Einstein condensate is then exposed to counterpropagating laser beams, which act to increase the interaction energy of the atoms with respect to their kinetic energy, until the point of the superfluid Mott-Insulator transition. When this transition occurs, the atoms are left placed in the lattice nodes, with the initial benefits of all existing in the same ground state. Further, atom displacement from lattice nodes, which occurs due to thermal interactions with the environment, is suppressed in the Mott-Insulator. In the case of neutral atoms, there are two main options to define the quantum states that make up the qubit system, based on the orbital occupation of the atom's valence electron, and whichever one is chosen determines how the states are initialized, controlled, and measured. The first option is to use Zeeman splitting energy levels to define the qubit. Zeeman splitting is due to the presence of a magnetic field. Using this choice of states allows for long coherence times, as it is robust. However, as a result, these states are sensitive to magnetic field noise, which can induce transitions. A more common choice of qubit states comes from using hyperfine splitting energy levels to define the qubit. Hyperfine splitting is due to the interaction between the nucleus and the electron cloud. These energy levels are a preferred choice for a couple of reasons. First of all, they won't be as affected by fluctuations in light or magnetic fields, which could otherwise result in phase accumulation between qubit states. And secondly, they allow the atom's internal and external degrees of freedom to be decoupled so that the trapping potentials don't affect the hyperfine spin states. Because these energy levels are well known, they can be initialized through optical pumping and can be read out by measuring fluorescence. In order to have a quantum computer, it must be possible to address the individual atoms in the lattice. As with many previous features of this system, there are a couple of choices of how to do this. The first is by using microwave pulses to control the hyperfine spin state of the atom. This is a method similar to that used to control any spin state in a magnetic field. Since all of the atoms are in the same state, a laser is focused on the specific atom to perturb its hyperfine splitting so that the microwave frequency is only resonant with that singular atom. The second method is to focus a laser beam on an atom, and that beam will directly change the hyperfine state of the atom itself. Microwaves are easier to control, but the optical-only method can result in a higher fidelity and faster gate operation if the source intensity is stable enough. A third important development to the use of neutral atom lattices as a qubit was the development of the Rydberg blockade. This was first successfully implemented to entangle rubidium atoms in 2010 by researchers at the University of Wisconsin-Madison and the Institut d'Optique in Paris. It is currently the dominant method of achieving entanglement in neutral atom lattices in order to create a 2-qubit gate. The Rydberg blockade is instituted by putting an atom in a Rydberg state, which is a state in which the electron cloud becomes very unlocalized and can span several microns. This creates the blockade, which prevents other atoms in the vicinity from being in the Rydberg state. The following protocol is an example of how to entangle two atoms to make a CNOT gate. So in panel A, state 1 is resonantly coupled to a Rydberg state, R, via an optical transition that is off resonance from the state 0. In panel B, you can see the implementation of a CNOT or controlled NOT gate, whereby the state of the target qubit is determined by the initial state of the control qubit. So if the control qubit is in the 1 hyperfine state, then the target qubit will be flipped, and if it's not, then it will not be flipped. And then in C, you can see the various entangled state outputs depending on the state inputs of the 2 qubits. The Rydberg blockade can also be used to entangle multiple atoms, which could allow for some interesting multi-qubit gates. Entanglement has also been achieved by colliding 2 atoms within an optical tweezer. However, this is not ideal as it requires physically moving the atoms together and does not result in very high fidelity as a result. Compared to synthetic qubits, it is very easy to produce unlimited identical qubits. So as a result, neutral atom lattices lend themselves to scalability. Since neutral atoms are weakly interacting with each other, the lattices can also be packed rather densely. A typical lattice constant for neutral atoms is about 5 microns, with which one could fit 10,000 qubits in a ½ millimeter given a 2-dimensional array. With a 3-dimensional lattice array, 1,000,000 qubits could be contained in a 1/2 by 1/2 millimeter space. As a result of being weakly interacting, they also have long coherence times, and researchers have been able to achieve coherence times greater than 7 seconds for an array of single atoms. Neutral atom lattices would be best suited for quantum information processing, and in addition, they have already proven to be useful for quantum simulations of complex solid-state systems. When compared to other qubit architectures, there are a few advantages that neutral atom lattices have over the others. First of all, neutral atom lattices are similar to another qubit architecture, trapped ion lattices. However, the long-range Coulomb forces of ion interactions can disrupt the qubit array in ion lattices, whereas neutral atoms aren't as susceptible to such disruption. When compared to superconducting qubits, since neutral atoms are cooled by reducing their motion, they do not require dilution refrigerators to reach microkelvin temperatures. whereas superconducting qubits require relatively large solution refrigerators to reach millikelvin temperatures. Further, since the atoms are optically controlled in neutral atom lattices, they aren't subject to sources of decoherence that superconducting qubits are by being coupled to wires. When compared to semiconductor defects, one advantage is that their location can be controlled and manipulated so that they can be arranged in any lattice configuration. However, as with all qubit architectures, while they offer some advantages compared to other architectures, there are some disadvantages as well. Trapped ions are easier to entangle precisely because of their electric coupling to each other. Superconducting qubits may require a lot of machinery to decrease noise, but they also boast far superior fidelity to neutral atom lattices, which is crucial to implement quantum error correction. And finally, semiconductor defects can also be studied at room temperature, but have even fewer requirements for stability, as they don't require a vacuum environment or powerful and precise lasers to trap them. As far as challenges to using the neutral atom lattice architecture, the trap lifetime is an important issue to address. When the atoms are in the traps are only as secure as the depth of the potentials, which is dependent on the power of laser. Although these lattices are formed under vacuum conditions, there are still enough air molecules present that their collisions with the atoms present a threat to knocking the atoms out of the potentials. In room temperature, an atom experiences a collision once every 100 seconds, and even at low temperature in a vacuum environment, an atom will only remain in its trap for a maximum of 1 hour. Crosstalk is when the quantum states of untargeted atoms are affected by performing a gate operation on a neighboring atom. Currently, even with highly focused beams that can select specific atoms, there is still a 4% probability that a photon would be unintentionally absorbed by a neighboring qubit, depending on the detector and the stats of the objective. This is too high to implement quantum error correction, unfortunately. The fidelity of two-atom gates in neutral atom lattices is another specific setback. Rydberg states are very sensitive to any stray electric fields and have a finite radiative lifetime, which is significant if the gate is too slow. So, one solution to the trap lifetime issue would be to have atom rearrangement hardware, whereby lost atoms can be efficiently reloaded into the lattice. The technology for this already exists as optical tweezers, so this should be something that is pretty straightforward to implement. To minimize crosstalk, there is a proposal to use a two-atom species lattice, in which cesium atoms are used for computation, and rubidium atoms are used for measurement. This would require this quantum state to be transferred between the two atoms. For fidelity, there has been theoretical work done by researchers at the University of Wisconsin-Madison to show that the pulse shapes can be optimized to decrease off-resonance excitation, and then, as a result, achieve fidelity as high as 99.99%. Theoretically, this percentage can be achieved with fast 50 nanosecond gates. The next step would be to implement this procedure and see if such high fidelity can be demonstrated experimentally. In 2018, researchers at Harvard were able to achieve 97% fidelity by engineering better lasers for a two-atom gate. So fidelity is getting closer to the required limit for quantum error correction, but is not there quite yet. The neutral atom lattice qubit architecture is well developed and has already successfully been used for quantum simulation. The next steps towards quantum computing are realizable, so we will be seeing continued progress with this quantum computing architecture in the future.